Alright, in this video we're going to be talking about how to find the length of a circular arc if we know the central angle. So going back to the definition of radians, and if you didn't watch the video I did on angle measure and the definitions of degrees and radians, I'm kind of falling back on that here to explain this, so you might want to check that one out if you haven't seen it yet. But if I have a circle of radius 1, right, the radian measure of my central angle is equal to the length of the arc that subtends that angle, right? So that angle cuts out a piece of my circumference, and the length of that piece of the circumference, which we call the arc, right? The arc is a fraction of your circumference. So the length of that arc is equal to the radian measure of that angle, right? That's the definition of a radian measure for an angle, all right? Now, we can extend that idea though, because what if our circle doesn't have a radius 1, right? Most circles don't have a radius of 1, they have a radius of something else. Well, the same relationship applies, it's just that, it's like proportional. So if I have a circle of radius r, where r can be any positive number, so if I have a circle of radius r, the length of the arc that's cut out by a central angle theta, s is equal to r times theta, right? So s is the length of the arc, r is the length of the radius, and theta is the measure of the central angle in radians, right? Very important. This doesn't work if your central angle is measured in degrees. It only works if your angle is measured in radians. And the reason it only works for radians is because it comes from the definition of a radian, right? With a circle of radius 1, the arc length is equal to the radian measure of the angle, right? It's not equal to the degree measure of the angle, it's equal to the radian measure, right? So if I make the circle bigger and my radius gets bigger, well, if I just multiply that angle times that radius, that's going to give me the arc length. All right, so s is equal to r times theta. S is your arc length. R obviously is the radius. Theta is the measure of your angle. Angle must be in radians, right? I put it up here in big bold letters. I've said it 2 or 3 times already. You have to have your angle in radians. If you're doing one of these problems and they give you an angle in degrees, the first thing you have to do is convert it to radians, and then you can proceed to use this formula, right? But this formula only works when theta is in radians. And if you don't know how to convert between degrees and radians, that video that I mentioned before on angle measure and the definitions of radians and degrees, in that video I also explained how to convert between one and the other, so you can check that out. But I think in one of the examples that I'm about to do, we'll have to do that. So if you haven't seen that yet, you'll probably see it in a minute or two when I do one of these examples. All right, so that's what I'm going to do now. I'm going to pause this, erase all this stuff, and put up an example or two where we use this formula to calculate the arc length or the radius or whatever it is they ask us to find. All right, so our first example here, we're asked to find the length of an arc of a circle with radius 10 meters that subtends a central angle of 30 degrees. All right, so let me draw this circle. To do one of these problems, you don't have to draw a picture of it. I like drawing pictures, though. I like having a visual representation of what's going on. So if it helps you, go ahead and draw a picture. But just know that it's not necessary. As long as you know what the formula is and you know what to plug in for each value in the formula, you can just go ahead and do it without actually drawing a picture. All right, so we have a circle of radius 10 meters. All right, so my radius is 10 meters. My central angle is 30 degrees. And I'm looking for the arc length, s. Well, s is equal to r times theta, right? So if I just do 10 times 30, that's 300. So s is equal to 300 meters, right? Wrong, right? I just said this, 3 or 4 times a couple minutes ago. This formula only works if your central angle is measured in radians. This one is measured in degrees, and so we can't just do 10 times 30, the radius times the angle, and get our result. First thing we have to do is change 30 degrees into radians, and then we may proceed and put that number in the formula and get our answer. All right, so let's change 30 degrees into radians. All right, which again, I did a video on this. It was about angle measure and radian and degree measures of angles. But just to quickly go through it, right, 30 degrees, remember, the conversion fact that we use for converting between radians and degrees is that pi radians is equal to 180 degrees, right? That's half of a circle in radians or degrees. It's pi radians is 180 degrees, right? So when I convert, I multiply by a fraction that involves the 180 and the pi. It's just a question of which one goes on top and which one goes on the bottom. And if you watch that video I did, you'll recall, hopefully, that I said, well, whatever measure you're starting with, in this case we're starting with degrees, I have to put the degrees in my denominator so that it cancels out that unit, and so I'm going to put the pi radians in the numerator, right? If I have the degrees in the denominator, the degrees cancels out degrees, and I have 30 pi over 180, which I can simplify. 3 goes into 18 6 times, so that's going to be pi over 6 radians. Right, so 30 degrees is the same as pi over 6 radians. Right, and these numbers here, and I said this before when I was doing videos on the unit circle, you start to see the same numbers over and over again. Like you'll see again at some point that 30 degrees and pi over 6 radians are the same thing. And at some point you'll see it so much that you'll just remember, oh, 30 degrees, that's pi over 6. Right, think about it. If I do 180 divided by 6, that equals 30. Right, pi is 180. So if I put the 180 in for pi, 180 divided by 6 gives me the 30. It all kind of makes sense, right? All right, so instead of 30-degree angle, let's call that a pi over 6 radian angle. Right, now I can calculate my arc length, right? The formula is S equals R times theta. My radius is 10 meters. My theta is pi over 6 radians. So I do 10 times pi over 6, which is going to be 10 pi over 6. And I can simplify this because 3 goes into 6. 2 goes into 6 3 times, and 2 goes into 10 5 times. I said that backwards and confused myself for a second. Right, so I'm going to divide both the 10 and the 6 by 2. Gives me 5 and 3, so I get 5 pi over 3. And my distance was measured in meters up here, and so the length of my arc is also going to be measured in meters, right? Whatever units I use to measure my radius, I'm going to use the same units to measure the distance of my arc length. All right, so if I have a circle of radius 10 meters and a central angle of 30 degrees, my arc length, right, the distance that angle cuts out from my circumference, is 5 pi over 3 meters, which if you're interested, you could put that into a calculator and get a decimal value for that. So that's what we have for this one, right? So that's our first example of calculating arc length. The key thing, two key things. One, knowing what the formula is, S equals R times theta. The other one is if they give you the angle in degrees, you need to convert that to radians before you can put that angle measure into the formula. If you can do those two things, then that's it. You're just putting in two numbers and multiplying them together and then simplifying. That's all it really is, okay? So that's our first example. I'm going to pause this and erase this one and put up another one where I think the next one they ask us to either find the radius or the angle measure, so we'll see what that one looks like. All right, next example here, we are told a central angle theta in a circle of radius 4 centimeters is subtended by an arc of length 6 centimeters when we're asked to find the measure of theta in degrees. All right, so once again, not necessary, but I like drawing pictures. So we have a circle of radius 4 centimeters. We have a central angle theta that we don't know the measure of, and it subtends an arc of length 6 centimeters. Right, so our radiuses are 4 centimeters, our arc length is 6 centimeters, and we want to find the measure of that angle theta in degrees. So once again, our formula is S equals R times theta. Right, and my S is my arc length, so that's 6, equals the radius, which is 4, times theta. All right, and now I need to solve for theta. So, I mean, this formula, the first example we did, we plugged in the numbers for R and theta. We just had to multiply them to solve for S. They could also give you, like they do here, S and R and ask you to solve for theta, or give you S and theta and ask you to solve for R. Either way, I mean, it's not hard. All I have to do to solve for theta here is just divide both sides of the equation by 4. It's a basic linear equation. The formula for this is a linear formula, so it's not like it's real hard to solve for whichever one of the variables you're trying to solve for. All right, so I divide both sides by 4. I get 6 over 4, so I have theta equals, well, I can simplify 6 over 4. So theta equals 3/2 radians. All right, remember, the theta in this formula is always measuring radians, but they asked me to find theta in degrees. All right, now if they ask me to find theta in radians, theta equals 3 over 2 radians, and I'm done. That's the whole thing. All right, but since they asked me for it in degrees, I now have to change 3 over 2 radians into degrees. All right, so once again, just like in that last one, pi radians equals 180 degrees. But now I have to multiply it the other way around, right? I have to flip over that fraction, right? Because now I need to cancel out the radians. So I need to put the pi radians in my denominator and the 180 degrees in my numerator. Now my radians will get canceled out, right? Cancel out that unit. And what I'll be left with up here is degrees. So my answer is going to be in degrees, right? So I get 3/2 times 180. Oh no, I get 3/2 times 180 over pi. So this is actually going to be kind of ugly. Well, the 2 can cancel out the 180 and give me 90. So 3 times 90 is going to be 270 over pi degrees, right? The radians cancel out, but the pi doesn't, right? Because my answer here that I got from over here didn't have a pi in it, so my pi doesn't get canceled out. So I get 270 over pi degrees. Right, now what I'm going to do is put that in the calculator. So if I'm trying to picture how big that angle is, like if you tell me it's a 30-degree angle or a 40 or a 150-degree angle, like I can picture how big those angles are. I have some idea of what you're talking about. I can't picture a 270 divided by pi degree angle. Like I just don't know what that's going to look like. So 270 divided by pi, if I put it in the calculator, is about 85.9 degrees, give or take, rounding it to 1 decimal place. So that's about 85.9 degrees, right? And I have a pretty good idea of what an angle of 85.9 degrees looks like, right? That's almost a right angle. It's almost 90 degrees, so the angle is going to look something like that, all right? Whereas if I leave it like this, that's kind of unsatisfying because I have no idea what 270 over pi actually looks like. All right, so that's using our formula for the length of a circular arc. You know, the first example, they gave us the r and the theta. We had to change the degrees into radians in order to use the formula, but then it was just multiplying the two. This one, they give us the s and the r. We had to solve for theta, so we had to just divide the 4 to the other side. It's not a big deal to solve for the theta here. But then since they wanted degrees, we had to go through that extra step of converting from radians to degrees, which we did, and we got our answer. All right, so that's length of a circular arc. Now, I'm going to do another video where I talk about like angular speed and linear speed that uses this formula. So check out that one to see some of the applications of the length of an arc.